Okay, hello everybody. Today we're going to be listening to a talk by Zurab and Janelidze. It will be on Isbell's subfactor projections in a noetherian form. And yeah, today we're going to try for the first time to do something on the whiteboard. So as soon as anybody can't see, please do shout. But hopefully it's close enough now for it to be visible online.
Great, thank you. There's a paper by John Isbell, published in 1979, called Tassenhaus theorem supersedes the Jordan-Hölder theorem, which makes a few remarks about the famous Jordan-Hölder theorem for groups. That states that if you have in the simplest form, it states that if you have a finite group, you can find a chain of subgroups where each is normal with the next one, and this is maximal. But moreover, if you have two such chains, there's isomorphic in a suitable sense. And the paper of Isbell discusses the sense in which they are isomorphic and makes some stronger claims than usually claimed in the literature. Although out of the three claims that he makes, one of them is actually a mistake. And in this paper that is the background for the talk, we're going to see how, first of all, the correct claims of his can be generalized to a context called the noetherian form, which is a special kind of a functor. And then, secondly, give a counterexample for the claim that's not correct. Okay, so let me begin by introducing the most important concept for the talk, which is something very familiar in classical group theory, the concept of a subfactor. So if I have a group G and I have two subgroups, X minus and X plus, it's called a subfactor if X minus is normal in X plus. So the pair X minus X plus is called a subfactor in this case. And we really want to think of this pair as a piece of the lattice of subgroups of the group, consisting of all the subgroups bigger than X minus and less than X plus. So it's really an interval. And we might consider these intervals even when X minus is not necessarily normal in X plus. Then there is a notion of a projection of one subfactor in another one that Isbell defines. So if I have two subfactors, X given by X minus X plus and Y given by Y minus Y plus, then the projection of Y in X, which I will write this way, is given by the following pair. So we take Y minus, we intersect it with X plus, and then we multiply that by X. So these are subgroups, so we multiply the subgroups by multiplying all the elements and taking the corresponding set, which turns out to be a group in this case.
What is X?
X is an interval of subgroups.
How do I multiply by an interval?
Well, you don't. Sorry, a mistake. You multiply by X minus. Thank you. And then on this side, we have something similar. So you see what happens here is that actually it's maybe nice to make a drawing for this. So if Y plus is here and Y minus is there. So this is our interval of subgroups. This is X plus, X minus. What we do with this process of projection, we want to somehow fit this in somewhere there. So, and the way we do it is to fit each of these in the same way. So, for instance, if I look at Y plus, I intersect it with X plus. That already makes this thing less than X plus. And then I join it with X minus. which then ensures that it's not just less than x plus, but also more than x minus. And of course, this is going to be join of subgroups because x minus is normal in x plus. Okay, so after that, Isbell proves the following lemma, which is the main observation from which all others that he makes follow. That if we begin with two subfactors, so given two subfactors, x minus x plus and y minus y plus, which we call x and y. If I project y in x and I project x in y, then these two things will project onto each other. So if I take a projection of, let me actually pick the pair that I use for later formulation of the lemma. So if I do this, yx and then y, this is projecting y in x and then projecting the result of the projection back to y. This is going to be the same thing as projecting x and y. This is not quite the same what I said. Actually, what I said was the consequence of the lemma, but first we're going to look at this. Okay, so this is basically the lemma, and from this lemma, he derives a stronger form of the so-called butterfly lemma, which is a way to prove Jordan-Holder theorem using, a way to prove Jordan-Holder theorem that was introduced by Zassenhaus quite a long time ago. And then also, thanks to this stronger formulation of the butterfly lemma that's deduced from this, the refinement theorem, and then as a consequence, the Jordan-Holder theorem will be a stronger form. Okay, so the context in which we're going to generalize Isbell's results is that of a noetherian form. Which is a functor that abstracts the specific functor. So if you take pairs of groups, which is the category of pairs, GH, where H is a subgroup of G, we can assign to this pair the group G. So here, H is a subgroup of G. If we call this functor F, then the fiber at each object G of the functor will be all the pairs GH that map to G. So in other words, there will be all the pairs GH with fixed G. So there will be exactly all the subgroups of G. And because group 2 is a category, this will actually be not just a set, but it will be a poset. It will be the poset of all subgroups, or actually the lattice of all subgroups of G. So the idea of this general context is to recover theorems of group theory, not just by working in a category that behaves as well as the category of groups does, but in fact working with a functor where for each object G in the category, this lattice behaves like the subgroup lattice should. And the syntax of this context, we can view this as a logical context, and the syntax of it is almost identical to the syntax of classical group theory. So the rest of the talk, I'm actually going to be talking about groups and subgroups, but what I will mean is the more abstract interpretation. Okay, before I move to discussing these results, though, let me remind you what are examples of noetherian forms. So where is this more general theory applicable? Okay, so they include all categories of group-like structures, which means things like vector spaces, or more generally modules over a ring, groups themselves, non-unitary rings, algebras over rings, and many others. The list goes on. It includes Lie algebras, Boolean algebras, Hating semilattices, cross modules, compact Hausdorff groups, co-commutative Hopf algebras over a field, and so on. So this is one class of examples.
Sorry, so in all cases, this category there appears.
In all cases, so in each of these cases, I have to suitably choose what will be the subgroups, the substructures. So I have to suitably pick this category. In this class of examples, this class of examples actually comes from things called semi-abelian categories, where the choice is canonical. I just take the subobjects in my category. Then there is another class of examples where maybe I'll use this side. Which is given by the categories of distributive lattices, but the morphisms should be chosen in a suitable way. They're not just lattice homomorphisms. There's special kinds of Galois connections. Also, modular lattices will work. And some others, which I'm going to skip now. This class of examples comes from so-called Grandis exact categories. There, we actually choose normal subobjects as the subobjects. So in some sense, they're closer to abelian categories, but big difference is that these categories do not have products. So they're kind of product-free version of abelian categories. And then there are some other examples as well that I'm not going to list now, but for instance, the dual of the category of pointed sets also has a noetherian form because it's a semi-abelian category. In fact, even any topos in any algebraic category will have a noetherian form by a result of Francois van Niekerk. However, that specific form is not very interesting for these results because the subnormal series in German hold the theorem trivialize. Okay, great. So what I discussed so far was an introduction. I forgot to put the title there. I promised myself to be very organized and put titles, but I didn't. And now we're going to talk about some preliminaries. I'm actually following the structure of the paper that was recently submitted. And I think I forgot to mention that this paper is a joint work with Amartya Goswami and our joint student, Kishan Dayaram, who recently very successfully defended his PhD thesis. Preliminaries is more of the paper than the rest, but for the talk it will be the other way around. So it's just recalling the context of noetherian forms. Since I promised you to talk in the language of group theory, I'm going to skip over that. I will just point out two or three theorems that we will use later. So the first one is the standard lattice isomorphism theorem, which in group theory states that if I have a group homomorphism, so if I have a group homomorphism F from G to H, then the following two intervals are isomorphic. The interval starting at kernel of F, or going all the way to the top, and the interval starting from the smallest subgroup of H, which I write as 0, going all the way to the image of F. And of course, this is what's responsible for the first isomorphism theorem, because we can quotient out and then we'll get the same group. Then the second result. So all of these results I'm going to mention, they hold in noetherian forms. There one needs to prove them, derive them from the axioms. In group theory, they are standard facts. The second one is actually I'm going to come to the second one a bit later. The third one will need a preliminary definition, which will need for me to move to the next board. So we are getting cameras in this venue soon. So, yes.
Is H just another group? It's not a normal subgroup.
In this case, H is just another group. Thanks for the question. What is a zigzag of groups? Well, it's just a diagram consisting of a sequence of groups, G1, G0, G1, G2, and so on. But they're connected by homomorphisms. These homomorphisms do not have to be all directed in the same way, so they can be either directed left to right or right to left. And that's the reason why I don't put arrowheads, because I allow flexible direction. Now, if I have a subgroup, let's say X of G0, I can take this subgroup that lives on in one end of the zigzag, and I can push it all the way to the other end of the zigzag. This is called chasing of subgroups, which was a technique introduced by MacLean almost at the beginning of category theory. So how do I do that? So what I do with X is that I apply these F's to it, right, in succession. But now, if all of the F's were facing right, then this expression would have been just interpreted the way it's written. So the direct images of X under F1 and then direct image of that under F2 and so on. But some of them face opposite. So I'm going to put a star here, where a star is either nothing, or star means take inverse image. So if the homomorphism is backwards, we take inverse image. And then, of course, we can do also chase some subgroup from Gn to back to G0. So given X a subgroup of G0, this thing is called the result of chasing X along the zigzag. The zigzags play the role of relations between groups. You see, in isomorphism theorems, you get some canonical isomorphisms in isomorphism theorems, and they can be built as first as relations, which then turn out to be homomorphisms. And typically, how they're built is by composing homomorphisms either in the correct direction or the opposite direction. As soon as there is one opposite direction, it's no longer a homomorphism. But if we compose it many times, sometimes the overall thing ends up being a homomorphism. What I forgot to mention is that the context of a noetherian form is self-dual, and that's actually the power of it. All the axioms on this in this logical concept. So this is something interesting from the perspective of logic, right? So imagine having a theory where you have a way to swap formulas from one with each other in such a way that the axioms are invariant under the swapping. Like the theory of a lattice, for example, is such. If I swap less or equal, it becomes, it's still a lattice. A category is also such a structure. A projective plane geometry is such. Lines and planes can be swapped with each other. The axioms are invariant under duality. So noetherian form has this invariance. And because of this invariance, some things will obtain more general form than how we see them in group theory. Because one thing in group theory that's definitely not invariant is being a normal subgroup. So every homomorphism has a kernel that's a normal subgroup, but its image is not a normal subgroup. And the kernel and image in this context turn out to be dual to each other. So because of that, the length of these zigzags in our general theory usually will be longer than what is necessary in classical group theory, where in most cases, in all cases, actually, zigzags of length 2 are already sufficient to recover all possible relations. Okay, related to this concept of a zigzag, we have a corollary of another thing that I'm not telling you, but the corollary states that the interval 0, 1 in each of the two ends of the zigzag ends of a zigzag, so this could be any zigzag, is invariant under tracing backward and forward along the zigzag. If and only if the zigzag induces an isomorphism between its ends. In this case, this would be G0 and Gn. If I copy my zigzag, what I'm saying here is that for me to be sure that the composite of these relations will give me an isomorphism from G0 to Gn, all I need to check is that the bottom and the top subgroups chase to the bottom and top there, and the same holds backwards. Okay, now you can ask me, all right, but how do we construct the isomorphism? Well, the isomorphism is constructed using an interesting pyramid construction that almost basically like builds a pyramid over this by things called pullbacks and pushouts. It's a very complicated construction in some sense, but also beautiful in another sense. But I'm not going to discuss this today because I've given another talk in the same seminar. And if I discuss this today, then I won't have time for anything else. So for us, we can just think of this idea of the induced isomorphism to be just the composite of these relations. This corollary actually has quite a pretentious title. It's called the universal isomorphism theorem. And the reason why it's called so because all the isomorphism theorems of group theory can be derived from it. So it turns out that every time I have a classical isomorphism theorem, I can find a suitable zigzag to which I apply this corollary, and I get isomorphism of the isomorphism theorem. Great. At some point, I need to keep track of my time. Fantastic. Thank you. Okay, so now let's consider a pair of subgroups. In other words, a subfactor. It gives rise to a zigzag. Which zigzag? So if G is my group, I can embed in G the subgroup Y, now seen as a group of its own. And this embedding is called iota Y. And then I can project from Y to the quotient group, Y over X, by quotient out by X. But this X now comes from G, right? So first I need to chase X from G to Y, and then quotient it out. So this will be quotient of X chased from G to Y, and that will be iota Y inverse of X. Yeah, so I think this is good. Okay, so this will be a surjective homomorphism, that's an injective one, so hence the tail and the special arrowhead there. This is one of the simplest kinds of zigzags we get. And then the next lemma that I'm not going to write out, I'm just going to speak it out, says that we can recover this interval from the zigzag by taking 0 and 1 here and chasing it backwards, which is kind of obvious. So the interval xy can be recovered from this zigzag by chasing 0, 1 backwards. All right, so if I take 1, right? This is a surjective group homomorphism. So inverse image of 1 is going to be 1. 1 refers to the largest group. And then I've got the largest group here, and if I take its image along the embedding, of course I will get 1. If I take the smallest subgroup here, inverse image will be the kernel, which is exactly this. But remember, x was less than x, so I get something here that's x was less than y, so I get something here that's less than y that comes from there. But because it's a monomorphism, it will go back to the x. Okay. In fact, there is a bit more. Thanks to the lattice isomorphism theorem, we also have that this interval of subgroups is actually isomorphic. Let me add that. The interval of subgroups is isomorphic to the subgroup lattice of y1 over x. So all of these things are, of course, very, very basic and standard facts in group theory. The reason why I'm reminding you of this is because it's just to emphasize that they also hold in the context of noetherian forms. Great. There is one more tool we need before we can generalize results of Isbell. And this is also a corollary of something that I'm not going to recall. This one is called, okay, it has a bit of a funny name. It's called less restricted modular law. And the reason why it's called so is because it's a corollary of something called restricted modular law, which is a bit more general. But that one is called restricted modular law because it's something that's less general than the modular law in lattice theory. So what does it state? If I have x, y, z subgroups of a group G, and I also have some other subgroup S of G, and we have the following properties for these subgroups. Y is normal in S, Z is contained in S, and Z is co-normal. Okay, what does this mean? Before I continue with the formulation of the corollary, let me just quickly say what co-normal is. So in this self-dual theory of groups, there is a notion of co-normal subgroup which is dual to the notion of normal subgroup. In classical group theory, all subgroups are co-normal. But because not all are normal, we still want to keep track of the co-normal ones in the general theory. So this restriction arises every time I generalize something from usual group theory. There is this restriction that sometimes comes in. For instance, already in the definition of this relation, I didn't say this, but already in the definition of this relation, I will require S to be co-normal as well. Okay, so if these three requirements hold, then the modular law holds for these triple x, y, z, which states that whenever x is less or equal to z, that implies that x joined y meet Z equals X join Y meet Z. Many of you are familiar with this law. You can think of it just moving brackets from left to right. It's actually a special case of distributivity law because X is less than Z, I can think of Z as X join Z. And then it says that X join over the meet is distributed, so it's equal to X join over Y, meet to X join over Z.
So is it easy to say what normal means in the general setting?
It's very easy to say what normal means in the general setting. So between subgroup lattices, you've got a Galois connection that arises from every homomorphism. And that's sort of the vibrational property of the functor. And normal is just take inverse image of the smallest subgroup in the codomain. Inverse image means to the right adjoint. So subgroup is normal when it is, so let's recall that. Recall that A is normal when it is of the form A equals some inverse image along some homomorphism of the smallest subgroup. And the dual of that will be direct image of the largest subgroup, which is, every subgroup is a direct image of some homomorphism. That's why everything is conormal in group theory. Thanks for that. But does that answer your question? Okay, so now we're ready to work with Isbell's theorems. So we move to the next section, which is called generalizing Isbell's subfactor analysis. Actually, in the newer version of the paper, the title is a bit different, but that's fine. I think probably the most important thing I want to show you is how to prove that lemma that I promised you. That is the most important piece of the puzzle. And I hope that I will have time to do that. Okay, let's see. Let me actually switch directly to the lemma to make it a bit quicker. To the proof, actually. So proof of lemma. It's 3.1 in the paper, but it is that lemma that we had on the first board. So let me put 3.1 there as well. So this will be a proof in the noetherian form. Isbell himself proves the lemma for groups using elements of groups in most cases. And sometimes it's a challenge to know how to translate the element-based proof to a categorical proof. And it turns out that this corollary 2.12 was the main discovery we needed, the main realization we need to make, that we actually need this thing and then after that, the proof becomes very straightforward. Okay, so here is the proof of the lemma. Can we again move to anyway, I make you stand around. Thanks. Okay, so I think we've already got the lemma written the way I'm going to approach it. One thing I want to add to the formulation of the lemma that wasn't needed for groups, but actually was also needed for groups, but I forgot to add that, is that X is a subfactor. So we had two intervals, but they were not just arbitrary intervals. X was a subfactor. I think Isbell requires both of them to be subfactors, but only one of them is named. there is also an addition to the conclusion of the lemma that this is yx is a subfactor provided x is a subfactor, which it is, and also provided yx plus is conormal. So this requirement is a technical requirement that comes out as a necessity for moving to the general context. But in group theory, we can just drop this requirement and then we get exactly the formulation of Isbell stuff. Okay, so let's actually prove this. So the idea is to be able to follow the proof. So if there's something not clear, please let me know. We begin by computing yx y plus. So yxy is an interval, and plus is the top part of the interval. The way projection is defined is I take the top piece of this interval and project it into y. So that's the same as yx plus y. Then plus can be inserted inside one more time. So that's the same as this.
The data is missing somewhere here, actually.
I don't think it's missing anymore. So
How can you times by y again?
yeah, this is no longer times. This is now projection. It's a notation that we introduced right here. Yx.
Yx plus is not an interval.
No, that's true. So
It's not there.
this notation is actually a bit more general. It applies even when y is a subgroup, in which case it's just this one. And if it was that, then it would be that. So I explained that to get this operational projection, I need to do something similar to y plus as I'm doing to y minus. And that thing is called projection of a single subgroup into the interval. So I can rewrite this whole thing, yx as y minus x, y plus x. Okay. Yeah, sorry about that, but thanks for the mark. So these first few steps, I'm just expanding what the definition tells me. There's nothing major happening here. And then I'm just observing that this thing is actually going to be a subset of x plus y, because when I project something in an interval, as I showed you on the diagram, I always get something inside that interval. It will be less than the top of that interval. So this is lesser or equal to that, and that is the same as xy plus. So far we established that yxy is less than xy, sorry, yxy plus is less than xy plus. We also want the other way around. So now let's see how we establish it the other way around. So now let's take yxy plus, and we're going to expand it a little bit by applying the definition of projection. So it's so as we already remarked, this is the same as y plus xy. And so what is y plus x? It's projection of y in x, which means I take y plus, I meet it with x plus, and then I join it with x minus. And then I do the same thing to this long thing. Then I meet it with y plus, and I join that thing with y minus. Now in here, I can do a shortcut on the expense of decreasing my subgroup. But I don't mind decreasing my subgroup because previously I needed to increase it. Now actually I'm comfortable with decreasing it. So how can I decrease it? Well, I can remove one of the summons in the join. And namely, I can drop x minus here. If I delete x minus, it only increases the expression, right? Because it's joined. If I delete it, I will have something less than that. So then I get y plus meet x plus meet y plus join y minus. which of course is the same as, you see y plus appears twice here, so it's the same as x plus meet y plus join y minus. And that is the same as exactly projecting x plus inside y. So it's a projection of x plus inside y, which is the same as xy plus. So we now proved both inequalities for yxy plus and xy plus, so they're equal. Remember that we're trying to prove that the intervals are equal, right? Yxy interval is equal to xy interval. For this, it suffices to show that the top parts are equal and the bottom parts are equal. We prove that the top parts are equal. Now let's prove that the bottom parts are equal, and this is where, okay, this part is really straightforward. The fact that the bottom parts are equal was the little challenge we had at the beginning, which Kishan helped us to resolve. So we now look at yxy minus. For the same reasons as before, this is the same as y minus x y. And now we're going to expand this as well, which will be a similar expression as this, except that instead of y plus, we'll have y minus. So it's y minus meet x plus, join x minus, meet y plus, join y minus. Okay. At this stage, we have to do a little trick. We are now going to insert another term in this expression without changing the value of the expression. If we look at this part, we notice that all of these terms, the first one here, the second one and the third one, all of them are actually less than, sorry, not term by term. But I'm claiming that this whole thing is less than x plus. Why? Well, this is less than x plus. That is less than x plus because it's meet with x plus. So this whole thing is less than x plus, and then we are meeting that with something else. So this entire thing is less than x plus. Therefore, I can safely insert another meet x plus to this and add it to that. So I'm going to get that. I can regroup the brackets because we have meet and meet here in both cases. And inside here, I notice a term that has the following pattern. Something joined with something else and then meet with something else. And if you recall the modular law, I've got something joining with something and meeting with something else. They think this x here should be less than z in order for the modular law to work. And so for that, I need to make sure that this part is less than that part. But it is, because it's y minus and y plus there. I also need the fact that x is a subfactor in order to ensure that all these requirements of normality hold before I can apply the modular law. And then I apply the modular law, and I get the following. Some simplifications are in place here. So let's see. We have y minus meet y plus meet x plus, right? So y minus meet x plus is, sorry, not y minus, x minus meet x plus is x minus. So we'll have y minus meet x plus, join x minus meet y plus, join y minus. And now if I look at this term and that term, I have y minus joined with something that's y minus meet. Yeah, so the term disappears. I end up with x minus meet y plus, join y minus, which is exactly x minus projected into y. So it's x y minus. And then I have the chain of equalities establishing that yx y minus is equal to xy minus, which is what I want. Okay, so the second part of the lemma that I added later, the proof of that is rather straightforward. I'm going to skip that. So the main part was basically this calculation, which, as you see, up to all is actually not so difficult. Great. Would like to have some update on the time. Fantastic. And we have until 1 o'clock, right? Okay. Well. Okay. So in the slides I prepared, this was 3/4 of done. So I'm going to run out of time for. Actually, no, almost a bit less than 3/4. Anyway, what comes next after this? So once we have this lemma, we can establish in the same way as Isbell does. We can establish the refinement theorem. And let me very briefly tell you what refinement theorem is. So if I have a group G, I look at the largest subgroup, the smallest subgroup, and then if I have two series, let's say the X series, let's say X0, X1, X2, all the way. So Xn is going to be 0, X0 is actually G. Where every pair is such that this thing, the thing below is normal in the thing above. Okay. And I have another such pair, Y0, Y1, going all the way down to Yn. The so-called Shire refinement theorem shows that
They need to have the same name.
they don't need to have the same length, thank you, so this could be M. It shows that we can refine these further, so by inserting subgroups, so that they become what is called isomorphic. But it means that every interval will be isomorphic to one of the intervals on the other side. This is actually decomposition of numbers with prime numbers. So if you take G to be Zn, the subgroups will be so the quotients will be the prime factors once it's fully refined. Now, the whole point of Isbell's paper was to say that the isomorphisms that we get, let's say here and there, when the two series are refined, these isomorphisms are not just arbitrary isomorphisms. They are isomorphisms arising from the fact that these two things project onto each other, which means that when I project this in that interval, it equals that interval. So in this example, x2, x1 projected onto y1, y0 will be equal to y1, y0. So Isbell says that people don't actually remark that these isomorphisms are not random. They come from the fact that the intervals project onto each other. So not only this holds, but also the other way holds. The remarks we add to this is that when you have two things projecting onto each other, the zigzag story, the universal isomorphism theorem, gives their isomorphism. And that will be a quicker isomorphism than even Isbell establishes in his paper. So that's one remark we make. Now, another remark we make is that Isbell claims that when you refine these based on the something called butterfly lemma, which I didn't tell you, but which comes out from lemma 2.9, what you basically do there is that you take this entire series and you project inside each of these. So you do this on this side and you also do the other side. You take this entire series and you project it into each of these. As a result, you end up having two things that are not just isomorphic, but projectively isomorphic in the sense of Isbell, and that's kind of magic that is a straightforward consequence of the lemma. But now Isbell says that when you refine these series like that, that will be the coarsest refinement of the two series. In other words, if there was any other two that still also refines, they will be kind of obtained from the coarsest refinement by adding more subgroups. And that claim is false. And the counterexample for that takes us again to number theory. So if I take Z6, its subgroup lattice looks like this. It will be this isomorphic to the lattice of divisors of 6. And if I take this as one series, and I take this as the other series, and I refine them using Zassenhaus's technique of this projecting the thing into the other, what I actually get out will be this series. So this series will be the refinement of both the vertical one and the bent one. According to Isbell's claim, this should be the coarsest refinement. Why is it not? Well, this other series does refine the vertical one. And by Jordan Holder, this other series is isomorphic to this one in actually a projective way. But this other series does not refine this one. So it's weird that kind of Isbell missed that, especially that he says in his paper that when he showed these results to some mathematicians, they said, oh, all of these are trivial results, we all know about it, and in fact, you can even do better. And then Isbell says that the better they proposed were all false, even for vector spaces. But the same is true for his third remark. But this is just one remark. The other two remarks carry over to the general context. I think that is the end of my talk.
Okay. Any questions?
Did Isbell give a proof of the false claim, and do you know what the mistake was?
He doesn't. He gives a one-line argument which assumes that it's obvious.
Okay.
He actually claims before claiming this, he claims something else, of which this should be a consequence, but that other claim is also false, and the same counterexample works there. The paper also isn't really cited, by the way. One can't really find citations to this 1979 paper of Isbell in Advances of Mathematics. It's interesting. Maybe that's why nobody picked up the mistake. Nobody read the paper. Our goal was not to find a mistake, of course. We wanted to generalize the results.
So does the lemma to work for any modular lattice, but the point is you only need some modular lattice.
Yes, so generalizing these ideas for modular lattices is a work of Ore, which is published in Annals of Mathematics. There are two papers where he proposes abstract lattice theoretic approach to abstract algebra that's based on modular lattices. It comes from Noether's school and also Dedekin's. Dedekin was the first to define modular lattices, but they were forgotten and they were rediscovered by Birkhoff, Ore, and others. And then the next step in Zassenhaus's book on group theory is extending it from modular lattices to lattices where we have partial modularity of the sort that we're discussing here. But those contexts still have everything being conormal because, and because of that, when you move to the categorical context, you don't get self-dual aspects. So this is kind of the next step which keeps the self-duality of modular lattices.
Okay. Thank you very much.
Thank you. Nothing from the
I didn't see anything.
Thanks a lot for joining.